let's discuss the theories on reaction rates, particularly collision theory, transition state theory, and the factors affecting the rate constant. So the collision theory states that the rate of the reaction is directly proportional to the number of successful, and I emphasize, successful collisions per unit time. So that's number of collisions, successful collisions divided by unit time, in this case seconds. So there are many factors that can affect the number of successful collisions. So you could think of two things. No? One is the amount of collisions that are possible, and the amount of, or the likelihood that a collision will be successful. Okay, and so here is just a small list of some of the factors that can affect your successful collisions. If you have temperature, that of course means that you have particles moving at different speeds. Okay, so the faster they are, the more likely they are to collide. Concentration, the more of your particles that there are mixed in the solution, then the more likely that they will come into contact with each other and collide. Activation energy, of course, those requiring lower activation energy will require less energy in order to successfully react with each other. So the success rate is higher. The orientation, of course, increases the success rate if it's in the correct orientation. The physical state, okay, so whether the molecules can access the surface of a solid, or if they're homogeneously mixed in a gas or liquid, that can affect the rate of the reaction. So this falls into the category of number of collisions per unit time. Catalysis makes it easier, so it makes it more successful, the collisions. And chemical nature, of course, also like catalysis, affects the success of your collisions. Okay, so there are many factors affecting the rate constant. Let's take a look at one of the more quantifiable factors, which is activation energy. It's defined as the minimum energy required for the reactants to be converted into products. And in an energy diagram shown here, where energy is plotted against the progression of the reaction, which we call the reaction coordinate, the activation energy is the energy required for the reactants to be brought to this point. Okay, the amount of energy you have to input there in order for it to start turning into the products. Okay, and it's a minimum energy, which means that there could be higher amounts of energy required, or you could input more energy than the activation energy, but for one particle of reactant to turn into one particle of product, you need a minimum amount of energy, which we call the activation energy. Okay, so energy diagrams can show us both kinetics and thermodynamics of a reaction. And since we're dealing mostly with kinetics in this scenario, in this lesson, we'll only be looking at energy diagrams and how they relate to the activation energy. Okay, so as you can see, the activation energy is not dependent on the initial and final reactant and product, but rather the state of the reactant and a point here, which we call the transition state. Okay, so in kinetics, we involve the activation energy. Okay, so what does this mean for activation energy, and how will it affect the rate constant? If we decrease the activation energy, then it will make it much easier for the reactants to reach the state of products. So this slope will be much lower. We'll need little energy in order to turn our reactants into products. But if we have a higher activation energy, then this reactant will need to go up to a very high point. So it will have to absorb more energy than the activation energy on our left hand side in order to proceed to form our products. Okay, so if we increase the activation energy, we decrease the rate of the reaction because less of the reactants will be proceeding towards the products at a given temperature, assuming that both of these reactions are in the same temperature. And speaking of temperature, temperature also directly affects the rate constant by the kinetic movement of your particles. Since temperature is really just molecular kinetic energy, the faster that your molecules move, the more collisions that can occur. Okay, so if we have a higher temperature, more of these particles are within the range of our activation energy, and therefore our rate proceeds faster. And of course, that's followed by the rate constant, which means that we increase the rate by increasing the rate constant. And this is all given by the Arrhenius equation or the Arrhenius relation. The rate constant K, okay, so if you recall, our rate in our rate laws are equal to rate is equal to K times the concentration of A raised to a certain power, B if it's bimolecular, and etc. raised to a certain power, and the total of these exponents is your order of the reaction. Okay, so the rate constant K here can actually be computed through this formula: AE raised to negative EA over RT. A is our collision frequency factor. So this is a statistical variable that gives us the amount of or the frequency of your collisions. So the higher the value for A, the higher the rate of the reaction. The lower the value of A, the lower the rate of the reaction. E is just the base of the natural logarithm. This is a value that you can find in your calculators. EA is your activation energy. So as you can see, if I increase the activation energy, then this exponent gets bigger. However, it's in the negative sign. Therefore, it will actually get smaller. Now, so if you increase EA, this negative becomes much more prominent, and so your rate constant actually decreases. So increasing the activation energy decreases the rate. Decreasing the activation energy increases the rate. Temperature here, along with the gas constant R, okay, is in the denominator of our exponent. So if we increase the rate, or increase the temperature, sorry, if we increase the temperature, then the denominator will get larger. So the exponent will shrink. However, since we have a negative sign, it will actually get bigger in total for the whole equation. So your rate constant will actually increase as you increase the temperature. Okay, so increasing the temperature increases the rate. Decreasing the temperature decreases the rate. Okay? Yeah. So if we take the logarithm of both sides, so ln k will be equal to ln a e raised to negative ea over rt. Now, we can actually separate a and ea over rt, e raised to e negative ea over rt, by taking by simply converting them into the two terms added together. No? So ln of e raised to negative ea over rt plus ln a. Okay, and then by the law of your logarithms, you can actually bring down this exponent, and since ln e is just 1, we can just bring down the whole exponent. It will be negative ea over r, and then let's separate temperature as well, 1 divided by T, like that, and then ln A. So you can see it here. in this equation, which we call the linear form of the Arrhenius equation. And it's named that because it looks familiar. It's the linear equation. We have a variable y, which is ln k, a slope m, which is composed of constants, which is our activation energy and our gas constant, universal gas constant. 1 over t will serve as our x, so this is what we change in our variable. And ln a, which is a constant b. Okay, so this is how you will apply it to the experiment. You will be obtaining the ln k and the temperature of your reaction. And so you'll plot this in a linear equation. And what you should obtain is the slope, which is equal to negative EA over R. And by simply multiplying it by negative R, you can find the activation energy. Okay. So what are other factors that affect the rate constant? One thing I mentioned was proper orientation of the molecules, or the orientation of the molecules. And that's because molecules in 3D space are not homogeneous. They don't have all the surfaces dedicated to reaction. So there will be some collisions that will just bounce off. Okay, so for example, this is an organic reaction. So this is a little advanced, but you can see that one of these arrows I highlighted green to mean that this orientation of the molecule and this orientation of the reacting molecule has to be in the correct position to properly react. Okay, the others might not bump into the reactive side, and so they fail to react. So there's a probability that this will happen, and this is roughly one out of the many different orientations that it can proceed by. Okay, so if the surface of the molecule is less susceptible, no, so there's only, for example, 1 or 2 areas of the molecule where the attacking molecule can react with, then the rate will decrease. Okay, so this is something for more complicated molecular structures. No, so there are some molecular structures that can give you slower reactions based on the groups that are surrounding it. Okay. So the same goes for some inorganic reactions like nitrogen and oxygen, nitrous oxide and dinitrogen monoxide. When they react together, they form nitrogen and nitrogen dioxide. No? But only on a favorable collision. There are some collisions that will not occur and will just bounce off each other. Okay. So, one other theory on the reaction rates is what we call the transition state theory. And it states that the rate of a reaction is indirectly proportional to the energy of the transition state complex. Okay, so this is similar to activation energy. Okay, since activation energy is also indirectly proportional to your energy of the transition state, rate is indirectly proportional to your activation energy. The same thing for the energy of the transition state is also indirectly proportional to your rate. Okay, so for the reaction A plus B, C plus D, the transition state complex is defined as the simultaneous bond breaking and bond forming state of your reactant to product molecules. So, for example, when they interact A and B to form C plus D, there is a state, a transition state, usually symbolized by this double cross, where the transition starts to occur. And at that point, it's at the maximum energy that it can have for this reaction. And so, that's when you observe the the state of transition. Yung transition state complex. So to better visualize this, the transition state can also be found in our energy diagrams as the as this position, no? Okay, the maximum of our energy diagram. Okay, so as you can see here, methyl bromide reacts with chloride, and then they form a simultaneous bond breaking of bromide and simultaneous bond forming of chloride, and that position is the transition state. Okay, so at this energy, there is a certain transition state energy. If there is a high transition state energy, then the rate will be much lower. So it makes sense. It's quite similar to your activation energy. However, for your transition energy, if it's much lower, then the rate will proceed much faster. Okay. So other factors that affect the reaction rate include your chemical nature of the reactants. As you can see here, potassium and cesium are two metals within the same periodic group. No? However, cesium lies much lower in periodicity, so it's much lower in the periodic table. And in terms of reactivity, cesium as an element is actually much more reactive than potassium. Okay, so this all depends on the electronic and atomic properties of your reactants. So in this case, potassium and cesium don't really have any other atoms attached to them. They're really just metals. So what really depends, or what really differentiates them between each other in terms of reactivity, is the electrons. Okay, so the electrons in cesium have a higher propensity of being ionized, can leave right away in contact with water. However, for potassium, it takes time. It can even just simply burn there, and the rate will be much slower. Okay, so the chemical and physical as well as electronic nature of the reactants affect the reaction rate. So it depends really on what element or what compound you're using. Okay, yeah. This also affects the physical state of the the physical state of the reactants also affects the reaction rate. So reactions with more reactant molecules in close contact proceed much faster. And so here's the two examples. One with solid chalk, okay, in hydrochloric acid. So what we keep constant here is the acid now. Acid proceeds in the same concentration. However, the solid is different. They're both the same. They're still chalk, but one is in bulk. So you can imagine there's a surface area here covering the entire bulk chalk and coming into contact with your hydrochloric acid. So the rate is much slower because the rest of the chalk is hidden inside the solid. It still has to wait for its turn in order to react with the hydrochloric acid. However, for your powdered chalk, so you can see here, they're in bits, no? And by pulverizing or decreasing the number of, or increasing the number of particles that are individual fragments of your solid, you actually increase its surface area. Okay, so if you increase the surface area, there is more surface for the liquid to interact with your solid. Okay, and if there's more surface, then there would be more reaction occurring, and therefore there would be a higher rate of reaction. Okay, and another factor is the concentration of the reactants. Now let's say we have both bulk chalk, so we have a constant for our solid, but however, in this reaction with bulk chalk and acid, we differentiate, or we put different concentrations of acid On the left, we have dilute acid, and on the right, we have concentrated acid. Okay, so if we increase the concentration of acid, we make it concentrated, and therefore there is more of that acid to react with the interface of the chalk, so the rate increases. However, for dilute acid, there is less of it to go around, so it still has to make its way to the bulk chalk, and whatever's happening there will only be with the amount of acid that's present in the surface, no? So therefore, the rate also decreases. So the reactions with more reactant molecules present, higher concentration, means the reaction proceeds faster. But that, of course, means that the reactants have to be dependent, or the reaction has to be dependent on the reactants in order for concentration to be a factor. And that can be given by the rate law of the reaction. Okay. And lastly, the other factor affecting reaction rate is what we call catalysis. And catalysis is a whole other field in itself, but in essence, catalysts, what they do is that they increase the rate of a reaction. So there's already the answer, no? They actually increase the rate of the reaction, but they are not consumed. Okay? They are not consumed in the reaction, and therefore, if you look at the total equation of your reaction that you're trying to speed up with a catalyst, you will not see the catalyst being consumed in the reaction. Okay? It will not appear in neither the reactants or products. And you'll still get the same amount of catalyst, ideally, that you inputted as you progress the reaction. But what they do, in order to increase the rate of the reaction, is essentially lower the activation energy by providing an alternative pathway. And that alternative pathway can be either split into multiple steps, or they can be a modified reactant. So again, there's still multiple steps. Now you have to do the modification, and then it will still react with your other reactant and then product. And so you'll get multiple transition states, and most of these transition states may include your catalyst. But at the end, when it gets to the products, the catalyst will not be present anymore. Okay? So what this does is that this also produces different transition states, but also different troughs or minima, which we call intermediates. Okay? And so these intermediates are your semi-stable states, which prior to proceeding in another step will sort of represent an activation state for your reactant. So initially your reactant will react with your catalyst and then produce an intermediate, and then that intermediate will then be reacted again, producing another, and then producing the product. So you can have multiple intermediates, but they all have different transition states in between them, no? From reactants to products, you can have different intermediates and transition states, and a whole number of them depending on the catalyst that you use. So of course, catalysts can come in many different types. In our experiment, I think we'll be using a homogeneous catalyst, but I think even just the crystals of your Rochelle salt will already react with your product, no, your reagents. Okay, so the catalyst essentially is just dissolved in your solution. Okay, so this is one of them. For example, acid can be a simple catalyst that can propel a reaction to occur and form products, no? For heterogeneous catalysts, they also may contain a surface functional group that can affect your product and the transition state between your reactant and products. Okay? So, essentially, homogeneous catalysts can be dissolved in your solution, and heterogeneous catalysts normally are solids or have a different phase from your entire reaction. So for example, your catalytic converter in um, your cars, mostly um, notoriously stolen because they contain platinum or other heavy metals, um, actually serve as heterogeneous catalysts to turn your uh, combustion fumes from very um, noxious to um, less toxic emissions. No, so that's the purpose of your catalytic converter.